we have been doing yesterday and the day before, starting to look at what stationary currents are about. And we were looking at the concept of the current and the current density. You remember we did counting also here to talk about how do we assess the current through an area. And you know the current is a charge per time that is flowing. And the reasoning is here, instead of using this surface, actually, you could also use this surface and ask in a given time interval, how many charges will pass through there? So that depends on the speed of these charges. And the speed is, or the velocity of the difference speed velocity. Velocity has a vectorial component. The speed is just a magnitude. But we assume that this here shall be now aligned. They are going all into the direction that is here plotted horizontally. And if you wonder how much is passing through here, that depends on with which velocity they move in this direction r. And the distance that they can cover at a given velocity in a given time interval is this dr. So everything which is at dr away from, let's say, this surface will pass in this time interval eventually through that surface. So this is why you, in the end, have to account all the charges in this volume that is prescribed by the, on the one hand, by the velocity and the delta t of your observation, and on the other hand, by this surface area. So this gives you a volume where all the charges are in that will, in this time interval, cross this surface element. And so that is how you get to your current, because you are then looking what are the charges in this volume element, and that is given by the spatial current, spatial charge density, and multiplied by that volume, and that is this areal element times velocity times delta t. And this here, if you now take the delta E and delta t, you separate that again, because you know this, I mean, this will be here basically then your current density J. So this is also a vectorial field. And then, I mean, we're splitting up that instead of using the spatial charge density, we use here the number of the charge, and we use particle density n. Small n is the number of particles per volume. The capital N, we denote the total number of particles. So small n is particles per volume, and then we multiplied with the charge value, and that is in the end corresponds then to our spatial charge density. And then, of course, we said it could be that you have different types of carriers. In that sense, you have to account for that that you compose this space charge density from the different particle densities and the respective charges of the charge value of these carriers. So from that point, we moved on, and we were looking actually at two scenarios. One scenario not so closely, but we see that the charge, that the current, how we were looking at it, requires the velocity. And if you are in free space, then of course you also have a velocity, and you can give your current density also by taking the space charge density times the velocity. But if you look in the presence of an electric field, so if you're in free space, you know that if your carrier is moving at a given space, at a given velocity, it will just keep moving with this velocity, right? So if there's nothing, there's no force acting on it, it will just keep moving with this velocity. However, if you now consider that you have an electric field applied between 2 points and there's some charge, it might also come from further out, but then it enters here into an electric field, it will be accelerated. And you can compute, of course, the energy that is added, kinetic energy that it is added to this electric field, because you know the work is given by the charge, or by the charge times the voltage. So the force acting is charge times the electric field, and you can just use Newton's mechanic to calculate how much kinetic energy are you adding over this distance. And you will, however, see that your there will be not proportionality of the velocity to the electric field. So this is a scenario in free space. What we focus more is to look at the transport scenarios in conductors, where you are in matter. And there, what you have kind of drift model, and also the idea is that you have a kind of a whole sea of charge carriers, and you have, however, some matter in which these charges are kind of are floating around, or you have these you have your, they might not be evenly distributed, but in a random fashion, you have your atom and you have the nucleus, and there's quite a bit of distance and in between. So these charges can move there. If they have any given velocity, they can move through this matter, but eventually they will hit and collide with some of the nucleus, for example, of an atom, and then their kinetic energy will be taken out. So they eventually would be stopping to move. So they would get into rest. I mean, there are still some forces acting because they are mutually the electrostatic forces which are acting, but you would not really have any directed motion on average. However, if you apply some electric field over this material, then you have a force acting on these carriers and they will accelerate. However, once they are accelerated, they eventually will again hit some of the nuclei, and their kinetic energy will be taken out either completely or partially. They will be deflected in some other direction. So they will hit here, and then the the velocity will be reduced, and it will direct it in a different direction, and it will be at a different magnitude. But eventually, it will be accelerated according to the orientation of the E field again. And this is what this here is basically depicting here. You get an acceleration over as the time advances. This is of a single particle. You get of a single charge carrier. You get an acceleration. You have a collision. Some of the kinetic energy is taken out. It slows down. It will be accelerated. It has another collision. And these come at random times. But there is an mean time for this collision. And there's also then in the end a mean velocity that you have. You can average that over all these particles, and you average it over the distance, because this collision will happen at various distances. But if you look at the larger distance, and if you look at the assembly of all these charge carriers, then in the end you will obtain some mean drift velocity. Yeah, so you're working here with the mean velocity of these charge carriers. And what one finds is that this mean velocity that you have is actually proportional to the electric field applied, yeah? So, and it is proportional by a constant, and this constant is a material property, and this is mobility of the charge carriers, which is called mu. This is kind of a Greek version of an m. So this is a mu, and it is dependent on the charge magnitude, on this mean collision time, and on an effective mass. And by now relating this velocity to the electric field, we can insert, instead of taking the charge value times the carrier density times the voltage, we write in here now the mobility and the electric field that is applied to. And then we can relate the current density to the electric field. And this term here, that is the electric conductivity, sigma. Alternative to sigma, we can use, so we can also write the electric field, then that drops, or sorry, the electric field that is in place over this conductor, that you can also, of course, relate then to the current density. You just write 1 over sigma, and the inverse, this 1 over sigma, that you can also give as a rho here, that is then a measure for the resistance. So this is the specific resistance. And you see that is related to Ohm's law. As you know, Ohm gives a law that the voltage over some conductor is here proportional, or it is the resistance times the current. And these are some integral quantities. In the end, this is a global thing that does not have any vectorial property or any position property. But this current here, that is obtained by taking the surface integral, or the area integral, rather the area where that current is passing through, that integral over the current density. And on the other hand, the voltage is obtained by integrating the electric field over the distance. And you see there's this relation in the end. This here is a local form of this here. So this is the local Ohm's law. Okay, then we have compared that. Yeah, then we also looked at the Kirchhoff law for current. We had already for voltage. And there we put a balance charge, we put up a charge balance equation. The idea is that this here is some virtual volume. And within this volume, you have some charges, and you have also some current flowing into this volume specified by this current density, and also possibly flowing out. And if you integrate all the current density that passes through the surface over this enclosing surface, then that tells you whether you have overall an outflow of charges or an inflow of charges. And the outflow or inflow of charges obviously is an equivalent to the change of charges in this volume over time. So this change of charge over time, that you obtain by equating it to that influx or outflux of the current density through that surface. And so you have a charge balance equation which holds always true. And for our specific consideration in this, what we're looking right now, we are looking at stationary currents. And the stationarity means that there is, for any given volume, there is no change of charge over time. So this means it's stationary. So everything that flows in flows out also again. So you have some currents moving, but there is no nothing that is accumulating or being poured out of some volume. So that means our current is stationary, and that means the overall integral over this flux of current in this enclosed surface is 0. This is for the stationary case. This is not necessarily um, always in other scenarios, but for us it will be always the case because we are looking at stationary currents. Otherwise, if it is not, then it is not stationary anymore. So this, however, this is always true, no matter whether you're in the stationary or non-stationary scenario, this balance equation has to hold true. And if you look at the node in a circuit, if you have an electric circuit and you have the circuit you depict it by meshes and by nodes, and in any node you have currents flowing in and flowing out. And if you magnify that and you think of having here a connection of several wires, then you can apply this balance equation and integrate here over this imaginary, you take this imaginary volume, you have an enclosing surface, and you see what is current that is flowing out or in this volume. And because you have a circuit, the currents, the charges are only carried in the wires, only there where your surface intersects with this wire, only these surface contributions will also give contributions to the charge influx or outflow. And by that when you look at the current balance equation, that you can now take this surface integral over the current density, that will only give you contributions at the respective locations where you have an intersection of that surface with any of these wires. So this is given here. You only have to integrate in the end over these discrete events where you have a wire going through this surface. And this is here, these n wires from K to N, and everywhere you integrate here over the surface of the wire. And this, however, is nothing else as a summation of all the currents in the wires. And based on this balance equation, because you have no charge that is being then accumulated in there, in this volume, you find that the sum of all these currents turn to be 0. So this is your Kirchhoff current law. And this is also then, if you compare it to the other Kirchhoff law that we looked at, that was the Kirchhoff voltage law. So if you have some network here with a node 1, node 2, node 3, then you have also here a voltage U1, you have a voltage U3 and U2, and you have here currents. In this case, let's call it I sub A, I sub B, or whatever you like to call them. But the current, the Kirchhoff current law tells you that in this node, everything that comes in here must also exit again. So the sum of all these, and this is only 2, but you can hear 3, 4, 5 branches coming out. So the sum of all these currents add up to 0. That is a consequence of the charge conservation. And if you take any closed mesh within your network and add up these voltages, then they add up to 0. So this is in the consequence of the energy conservation, the Kirchhoff voltage law, while the Kirchhoff current law is a consequence of the charge conservation. And then we started with the next topic, and now I have to see, where is this? Oh, just a moment. I thought I started on that already, didn't I? Where did my notes go? Ah, here. Okay, sorry. Here they are. I was just not at the right position. So now we are interested in power, the electric power and the power transmission. So motivation is here, for example. You have on the one hand an energy generation, and you also have a consumption of energy. And we have seen the energy, that is the work, but if we consume it, then we consume, of course, the energy, but we can also express it in consuming energy over time, work per time. So that would be electric power. And how does it look on the very small scale level? How does it look if we are operating with single charges? So we know that the power is given by integrating the force over a given curve, a given path. And for a single charge, that means we can take a differential view here by taking only a very small increment, and we take a single charge and move that along some curve that is prescribed by this curve element, then the vectorial r. And this vectorial r by the force at this given position, that gives our increment in energy or work that we have to provide or get out. And the force is related that we know the E field is defined as the force per charge due to the electrostatic force or the Coulomb force per charge. This is the E field, so Q times E and times the differential element here. That is our increment on the electric work that we have to perform when we move some charge. And because we said the power is the consumption of energy per time, then we can also give that the delta of the work over delta time is the power. And if we do it on the differential level, then we take just the d of the work over the d of time. And this is the work performed per time interval dt. So this work here, we insert here that this is this q times e, and then we have the dr by dt here. And that actually is our, in this model that we had, because we're looking at these conductors, we know that this drift model applies, that becomes useful. I mean, and this is general holds true, but you'll see that this becomes not particularly useful because how we further develop that is, however, we see that basically that would be our velocity vector. So this holds true general. So the electric power of one point charge moving at the velocity v is given in this expression. Now we make use of that, what we have of our considerations that we have taken with respect to the definition of the current density. So we make a transfer here to what we have introduced earlier, and that would be that our current density, so the ampere second per square meter, square centimeter, so per area, that is the particle density n times the particular charge of these particles, and here the velocity. And there, you know, we work with a velocity field velocity vector, but in a conductor you can obtain that by this drift model, where you average the velocities of the carriers, and you can work here with your mean velocity. This is also nothing else. Carrier density is the total number of carriers per volume times the charge per carrier times the velocity. So we make use of this here. So our current density is Q times N over V. This is the volume. This is the velocity. And for 1 point charge, what is the electric power? Just take that from above. Let's charge, electric field, where it is moving through, and velocity. And now we want to see what happens if we expand that here with the total number of carriers. Then we get the number of carriers times this differential power contributions. That would be then charge times total number of carriers times the electric field times the voltage vector. And now let's expand that here on either side with the volume, or rather with the, we divide it here with the volume. Let's write that like 1 over volume. So that would give us number of carriers divided by the volume times the differential electric power times the charge, here also number over volume times the electric field times the velocity. And then we can rearrange that a bit. We write here the Q, the number, the total number over volume, that is particle density, small n, times the velocity times the electric field. And this one here, you will recognize the first three. This is, that's on the previous set of notes. But you remember that is exactly our current density. So you have here current density times the electric field. There also you have a dot here, right? This is a dot product because vectorial quantity comes from the velocity, and you need to take the dot product of the vectorial quantity here in the current density that is basically given through this velocity vector. And here you have what matters is component of the electric field, which coincides here with the velocity, with the direction of the velocity vector. So here, this here is basically your power for n particles, for moving n particles through the field. So if you take this here, the power over the volume, that you can also here denote with a small p, p electric, and that would be a power density. It's a power per volume. It's power per volume. So we can give now the electric power density, the power per volume of the current distribution, that is P electric. So actually I think we be more accurate because we want here the power density per volume, but we want it for all particles. So let's write this here, also the n here. And then we have the power density, the small p el for electric is equal to current density times electric field. Note the dot in there, that is an inner product. The power is also not a vectorial quantity, right? So the electric field and the current density are. And this would be our equation 2.27 if you refer to the lecture notes. So, okay, here it is again. Okay, the power density is small p electric, current density times electric field. That is for an ohmic current transport. If, so it is for an ohmic current transport if we have the current density to be equal the sigma times E. That is in alignment with this drift model. This is Strutz. It's the name of the person who established this model. This is this drift model that basically goes under this assumption that you have this kind of like a sea of electrons, and you have these nuclei, or lattice structure of the material, or doesn't have to be a regular lattice, but it's some kind of arrangement of your atoms, and in between are floating these carriers, and these carriers, however, undergo frequent collisions, and this is the Drude model, the Drude drift model. So now let's assume that we have this applicable, that we have a current transport according to this Drude model to this drift model, where we have these intermittent collisions. We have the carriers accelerated by the electric field, but then there come these collisions, and we have to work with the mobility, the average speed, that the average velocity that these carriers obtain is proportional to the electric field, and this proportionality is given via the carrier mobility mu that we introduced. And then we came up also that we have here exactly this here, that we have introduced in this model this conductivity. So that means our P electric, we substitute here the current density with the sigma E, and we keep the second E here, right? So you see this, you see also here, this is just a scalar product here, because this is also just a scalar quantity. You have sigma times E, you insert that here, but now you have here this inner product for E that originates from this part here and the other E here. So then you can rewrite that by taking here the magnitude squared. Excuse me. Otherwise, you can also basically, instead of substituting this here with sigma E, you can also substitute the E field here and take it, basically bring down the sigma here, 1 over sigma times the current density is equal to the E. So then you would obtain this formulation here, current density squared times 1 over sigma. And because it is ohmic transport, we have no power being generated. We have power here that is being used. So this will be here larger than 0. This is our equation 2.28. So for ohmic transport, this power density is larger than 0 because we have a power loss. And this is what we have, for example, in the scenario of the power distribution we had in the beginning. We have a power generator and we have a power consumer, and somehow we have to get that power there. So we have to basically move we have a power line that is connecting the consumer with the generator, and in this power line, but not only there but also in the consumer, you will have some ohmic losses. So this is power loss, and basically the power is being absorbed. This is a power dissipation, and as a consequence, where does this power, this is energy per time that is being absorbed or is vanishing, dissipated. In consequence, this will be converted in this ohmic transport into heat. This is where your loss power goes. So remember, this here is the power density. Let's look at some example. We want to look at the electron transport in a straight cylindrical wire. This is our wire. So you have at the end and at the beginning a surface of the area A. Inside here you have your current flowing, that's a J. Outside over the wire, or not, sorry, not outside, also inside, but along the wire this is also inside. I just draw it outside. But the from interface to interface, there's an electric field applied or running. It is there's a voltage applied. There's an electric field running from there, and the total length of this wire or the wire segment that we are looking at is L. So what we can assume here is that we have a constant current density over the wire, I mean over the wire cross section and also over the length of the wire, and so that our electric field is parallel, is aligned with the wire. So then let's look, we want to obtain the electric power density, which is the current density times the electric field, and that shall yield us then the also, I mean, that is the power loss, but we want to have the total power loss in this ohmic resistor, and that we obtain by now integrating this power density over the volume. And then we have the total power is obtained by taking the integral over the volume over the power density. And because it is constant over the entire wire, it becomes quite easy because we just have to take the electric power density times the length of the wire times the cross-sectional area of the wire. And that power density we know is here, right? This is current density times electric field. So let's rewrite that as current density times electric field. But then put the A here, the cross-sectional area, and the length we put here. And you recognize current density times the cross-sectional area is a current, and the electric density, the electric field over the length of the wire here is our voltage over the wire. So you have E times U. So we have the power loss in the ohmic resistor, and that is we call now R. And you can also, you know, that U is equal to R times E by Ohm's law. You can, of course, replace here the U, the I. The I is then U over R. Then this is U square R. Or you can also replace the U, and the U is R times E. Then you obtain R times E squared. That's equation 2.29. So this is how you obtain the loss in a resistor. Now I want to look at the efficiency of electric energy transmission. So you know, you have on the one hand here the generator where the energy is generated. This could be some some kind of power plant that could be a coal plant, that could be a gas or nuclear. Well, it doesn't look like a nuclear one, that particular, but it could be a hydro electric power plant where you have this dam and you want to use it here to draw the energy as a consumer, either from your plug point or you want to operate a train. So you have to bring your energy and bring your power from the generator to the consumer side. And for that, you need this distribution, or in particular, you need a transmission line here. Now, let's not go into a more complex distribution, but what you need is transmission here of your power. And you have here on the generator side what is provided by, for example, LED on the power station. You have a voltage UG for generator. You have here this power line that carries a current I, and of course the current is also being carried in back again. And then you have the consumer side. There you have the voltage at the consumer, And because you have some ohmic losses here in this power line, you can put this here with a equivalent lumped, a lumped equivalent circuit element, so to say. I put in here a resistor, an ohmic resistor, but of course, you know, it is distributed over the entire line, but in the circuit models, you kind of concentrate the properties and you make lumped equivalent circuits. And so you have some power loss in this transmission line. And as a consequence, I put in this ohmic resistor, but over this ohmic resistor, there's also a voltage drop. So we have the energy generation on the side of the plant, and that would be the U generator. And the power that is being provided here would be equivalent to the voltage at the generator side times the current that is being sent over the transmission line. So voltage and power at the consumer side, they are that U sub C, and the power, the current remains unchanged, but the voltage has changed. This is UC times I. Now, the resistance that has been lumped now, we have put that into a single resistance, even though it is, of course, distributed over the line. But in our equivalent model, it's a lumped resistor that is given with R sub L. And we know then what the voltage at the consumer side is. That is the voltage at the generator less the voltage drop that happens over the ohmic resistor, and that is given by the ohmic resistance and the current. So that would be our URL. That's the voltage drop over the resistor. And now the question is, how good is our energy transmission, the efficiency of the energy or of the power? We want to compare the powers that is provided or that is being available to the consumer versus what is provided to the by the generator. And this here is a eta, Greek letter eta. It's like an N, but it has this going down at the end. And so we insert now here. So we know the power at the consumer is this UC times I. And at the generator, it is, as you see here, UG times I. And you see that the I is actually canceling out here. And then we take this UC here and insert that here. Then we obtain UG minus RL times I over UG. And now we can say that the eta is 1 over, 1 minus RL times I over UG. Now we can also write that differently because we can expand here the second term RL times I. We can expand it with UG here and make it here also expanded UG square. And then if we do that, you see that we have UG times I. We have the power again of the generator. We can rewrite that as in minus RL times the power of the generator over UG squared. It is a different way of writing it, and that also has some advantage. So first of all, with respect to eta, that's the efficiency, and that is always smaller or at best equal to 1. Of course, you want to have the efficiency as high as possible. You would like to provide at the consumer as much power as you are providing at the generator side. So let's summarize that it is minus RL times P generator and divided by U generator squared. That's the equation 2.34, and that's the power transmission efficiency. And now you can, by writing it in this form, you can see what it is beneficial. If you want to maximize your power efficiency, you want to get your eta as close to 1 as possible. So that means this second term here, you want to be, this should be as small as possible here. And how do you minimize it? Of course, it is very good if you can reduce the resistance of the line. But since you eventually run also there into a limit, you cannot make the resistance of the line arbitrarily small. You see, another advantage is of increasing this efficiency is by making your generator voltage as high as possible. And that is why you have for the power transmission from the plant, but for the distribution from the plant to the consumers, you have these distribution networks which have a very high voltage, because this high voltage allows you to reduce your losses in the distribution. And then you have to, of course, this is not included here, but then you have to down transform it at the consumer side, because you don't want to have 10,000 or more voltage in your plug point, of course, even though you could reduce the losses of your devices. So RL should be minimized, and the generator voltage should be. But of course, in general, it is more complex. This was just a DC consideration with one, or with two wires here. Of course, in most cases, you have three-phase current, and there is much more to consider along with that than what I have given here in this example. But also, nevertheless, you also have high voltage direct current transmissions. They also have their advantages, and they have become possible in recent years, increasingly, thanks to advances in high power semiconductors. So you also can, however, use this here for high voltage DC transmission. This concept for the three-phase current, it will be a bit different. DC is direct current, and that is this high voltage direct current transmission is beneficial for minimizing losses. Well, that brings us to the end of chapter 2. Let's make a 5 minutes break. What do you think? Yeah? Okay, let's proceed. Let's proceed here. Now we want to look at this third chapter, and that third chapter actually is about magnetostatics. What are we covering? First, I want to give you a few examples about magnetism in daily life, then some observations, and some phenomenological derivations, and then also what is the content of chapter 3. So this basically should give you a quick overview. So there are quite a few examples where we encounter magnetism in daily life, and that you're all familiar with. So that could be, for example, just some magnets where we use to stick something on the board or hold some tools in place. But you also have here this scenario where you use this in more an industrial setup where you use strong magnets to carry loads. So of course, anything which is magnetic, so you can use them to lift things. You know that toy, like these trains, toy train that has a magnetic coupling here between the engine and the different coaches. And then, of course, you can use it in your loudspeaker. You need to set the membrane in motion. And of course, very useful is also the compass that helps you to navigate when you don't have your smartphone with you. But of course, also the smartphone has some magnetic sensing tool um, inbuilt often. So let me give you some video here that shows you some effects. So this is a video that you can find on YouTube, and that shows you some nice scenarios where you have magnetisms. Uh, so you see here two magnets, compass, metallic ball, non-RAM, that is what being used. And this person takes two permanent magnets, and you can see if you push them together, depending on how they're oriented, you have a repulsive magnetic force. So these magnets are pushing each other away. And on the other hand, if you are orienting them the other way, then you have an attractive force. You see how the other magnet snaps here and actually holds on to that quite strongly. You can lift it up, so it's a quite strong magnet. And then you have a little ramp here. It is a top view. You let a little non-metallic ball roll down, and it just expands straight into this direction. But on the other hand, if you have a ball that is metallic and is a response to this magnetic force, you see how it is deviated from that magnetic force in its trajectory. So you see some materials are non-soft magnetic, others are magnetic also. And then you have the compass needle, and you see, of course, the compass needle makes use. It's a small magnet that is suspended on a pin so that it can freely rotate, and it makes a use of the very weak magnet field of the Earth to orient where the north or south is. But you see, if you bring this in close of a other magnet, then you kind of deviating here the needle. So put a multitude of compasses around that magnet, and you see their needles are not following the Earth magnet field, but they follow that local, much stronger field of that small magnet, and they orient themselves accordingly. And here you have one strong magnet. You put a sheet of paper on it, and then you sprinkle some small fragments of iron here onto that paper, and these little pieces of iron, they start to orient themselves, and basically showing you a nice picture that is recreating also what we then know as the magnetic field lines. Okay, so this what you have seen here are permanent magnets. They are made of a very specific material, and they are suitable. Whether they are suitable, this material, that basically depends of the structure of the material, whether it is suitable as a magnet. Then this magnetic force, when you have it, it can also act on specific materials like iron particles, iron nails, but not on all materials. So they are basically materials which don't have to be magnetic in the first place, but they are responding to magnetic forces, and they can be basically also to some degree magnetized. And very important, you have these two poles. That is somewhat a bit an analogy, but there's also some difference to the electric charge. And the charges, we have two flavors, plus and minus. The magnet has two poles. That is a north and a south pole, but there's a very important difference that I will come also to later. You basically, in electric charges, you have these two flavors, plus and minus, and you can separate those. But you don't have that option with magnets. Magnet comes always with a south and north pole, and you cannot separate those. So north, south pole, they attract each other, and north or south pole repel each other. So that north-south pole comes probably obviously from the magnetic field that we have in the Earth, which this magnetic field effect has been discovered long time that you can use it to help you navigate in the Earth. And of course, one would denote the pole of the magnet that points towards the uh, north of the Earth. That would be the North Pole. That, in consequence, of course, means that the magnetic field at the North Pole of the Earth actually is what we would call a South Pole. So this magnetic field, this can be described by a force field. This is so in analogy to the electric field. And the force depends on location and direction. It can be described by a vector field. So we have field lines, and also the forces. The force decreases with a ratio which is given by 1 over r squared. So you see there's quite a few parallels to the electrostatic scenario. But there's also some differences that we will see later also. That would be, for example, that you cannot separate these poles. So there's a very interesting discovery that was made by Hans Christian Ørsted, a Danish scientist in the beginning of the 19th century, and he observed that when he has a current flowing, then actually there's also some effect on the magnetism. So I show you this video. You have here a battery, and you see that battery as such, it does not have any magnetic properties. You can move the compass around and the needle will not be affected. It stays put to where the Earth magnetic field is. But now you connect here this wire to the two poles of the battery. So basically you short circuit this battery, but through this wire you have a current flowing. And now as you go with the compass to this wire, you see that the needle starts to spin around. So there's obviously some effect of magnetism that is associated with the flow of these charges. And now this is actually something that you can also very nicely reproduce. You take a screw or also some iron nail, and you make a lot of windings. This is here this isolated wire, and you wrap it around. You actually obtain a very strong electromagnet, and you see that when you move here, you have this current. As soon as current flows through this wire, there is a magnetic effect. You see it is not connected, is not able, it's not acting not as a magnet, but now as you connect it to the battery and you have the current flowing, it becomes a magnet, so you can switch it on and off. So you see already there's quite nice use for industrial application, but in the end also this is not only used for using your electric power, it is also, or energy is also, of course, used to generate them. So the phenomena and observation that goes back to the experiment that Ørsted did in 1820. He saw that there happens a deflection of the compass needle, just what you see in this video. Once you bring this compass needle close to a current carrying wire, so the conclusion is there seems to be a magnetic field around the wire, and there is also a relation between electric and the magnetic phenomena. So we have an electromagnetic interaction. The observation is that if you have moving electric charge, then this charge experiences a force in a magnetic field, and this charge, it will be deflected from that original curve. That will be the Lorentz force that will be covering in the sections to come. Then in terms of application examples, so we have seen already the loudspeaker. That is a very useful thing, but of course you can use electromagnets of all kinds, and as a consequence, then you use this effect also to drive your or build electromotors or also generators. You can use that in particle accelerators, like you see here, the picture of the CERN. There you use a magnetic force to keep electrons on a certain trajectory, and you accelerate them. And did you see these are very large setups that extend over many kilometers. And then also there are medical applications like the magnetic resonance tomography, where you can make use of the magnetic spin of particles to do an imaging and use basically that for getting scans of body parts without being here in any way invasive, and can use it for medical diagnosis, analysis and diagnosis. So the content of chapter 3 will be magnetostatics. That means we are looking at magnetism, but we also include the static. We stick to the static aspect, which means we are looking to effects which are time invariant. So that what we will not cover also, even though it is static, that will be the force between two permanent magnets, or the magnet itself, or the magnetizable materials. So what we'll be covering is the aspect, what is the physical origin of the magnetism or of the electromagnetic interaction? Why are some materials magnetic and why others not? And how are magnetic fields being generated? What is the connection between electrostatics and magnetostatics, and how can we describe this? And structural similarities and differences between electrostatic and magnetostatic phenomena. So these are the introductory slides, and I've uploaded those for you too. And I have some more slide here on the first section already, because now we want to look into this phenomena of this interaction of moving charge and the magnetism. And that means I want to look into the Lorentz force. So we have forces on moving charges in the magnetic field. This is based on a phenomenological observation. So how do we recognize here the presence of a magnetic field? Well, we do so by seeing an impact on a moving charge. And there's a deflection that is happening on to the charge, which is perpendicular to the motion and to the direction of the magnetic field. So we have a force perpendicular to direction, and this force is called the Lorentz force. So you have that plotted here, or let me give you also the formula along with it. So you have here this Lorentz force, which is denoted with F sub L. And you have here, what you see here is these are field lines of the magnetic fields, but they are coming out of the plane. So the common denotion is if you have lines coming out of the field, you make that a circle with a dot. That means it comes out here of the plane. If it goes into the plane, you make a circle with this cross here, then it goes in here. So you have these magnetic field lines coming out. You have here a charge which is moving through this magnetic field, and you see the direction of motion here is in the plane of the slide here, while the field is coming out of that plane here. So the motion is perpendicular to the magnetic field, and the charge has a given value q. So what applies here is the right hand rule. So you have a relation between the force is related to the magnetic flux that you have. This is a B field, this is a magnetic flux. It is proportional to the speed of, or to the velocity. I mean, proportional would be to the speed, but the direction is determined also by the velocity. So it depends on the velocity of your particle and of the charge of this particle. And you can use a right-hand rule. So you have here your velocity. If you point with the thumb in the direction of the where the particle is moving, and you take your index finger to point into the direction of the magnetic flux, which comes out of the plane here, then the third finger here, the middle finger, will give you here then the cross product. So this is your first finger, second finger, and the third here, the middle finger, that will give here now the direction of the Lorentz force. So we have first the field quantity, which is the cause for the Lorentz deflection. That field quantity is the magnetic flux density, which is also called the, or you can also call it the magnetic induction. That is also commonly called the B field. And you have a dimension which is given in Tesla, named after Nikola Tesla, the Serbian physicist. And you have here a unit which is voltage times second per square meter. You can compare that also. You see this is a flux quantity again, like we had the electric flux, the D field. The D field was ampere second per square meter. And now you have the magnetic flux density, that is volt second per square meter. And that unit is also given as Tesla. So in addition, or so we also have, so according to the electric field, the effect of the force here is described by a force field. So we have basically two quantities already. You see we have the force field. If we have an electric field also provided, then we have that what you already know, that is electrostatic force that is given on the charge, and that is proportional to the electric field. And you have the Lorentz force, which is here in the presence of a charge, and it is a moving charge, and it is given in proportion to the magnetic field, but it has to be a motion of the charge which is perpendicular to the magnetic field in order to experience a force. So now if you have both present, an electric field and a magnetic field, you can give here the total electromagnetic force on the charge as a superposition. So this is what we have already seen here from the electrostatic case. You have the that is, the force is oriented along with the electric field. And here you have a force which is oriented perpendicular to the magnetic field. And we call the second part here Lorentz force. Sometimes you might also find in literature that they call the whole thing here Lorentz force, and they say this is the first and the second part of the Lorentz force. But we shall call here the Lorentz force the second part here, so that depends on the magnetic field. Now, let's look at some aspect of the work. We have said that the work that is carried out is in the electric field, or in general, actually, it is given by integrating the force over the over your integration path, basically. And this is a differential element for the work. So it is the electric field and the differential line element. So for the electric force, that force is given by Q times E. So, and if we have now the charge moving in a magnetic field, then we have that work contribution possibly from that second force. But it is quite interesting because this is the second force component that we said particle experiences according to the Lorentz force, right? So we have the complete electromagnetic force obtained by here what we had seen already with the in view of the Coulomb force or in view of the electrostatic force. And this is a new term that we add to it. Now, if we have electric and magnetic field presence, we move a charge, then we have these two forces, and we want to assess what is the work that is being carried out. So that differential element is for the presence of the electric field. So we have seen that already quite a bit in the first and also the second chapter. Now we take into account the second contribution to the total work. So that will be the work in the magnetic field. That is now the force, the Lorentz force, and we integrate over the or we take here the line element where that particle is moving along. So you know that actually the velocity we can express as the time derivative of this line element. The particle is moving along, so we can write that as dr by dt. And if we then take the power in comparison, then we take the differential energy or the differential work element and divide it by the dt. So this would be our power in the magnetic field. And the interesting thing is now that actually this work is perpendicular. This force is perpendicular to the motion, the direction of motion. And respectively here, when we look at the power, the velocity is, so we have also this here perpendicular to the magnetic flux. In consequence, there is no work done on an electric charge in a magnetic field, and also no power is added as far as no field is present. So in this first line here up there, you see in the electric field, you have a power contribution, but here in the magnetic field, even though there is a force involved, the force is not in the direction of the motion, and hence there is no work or power being needed or added. So in consequence, the kinetic energy remains constant, and we also have a magnitude of the velocity vector which is not changing. So you're changing the direction of motion in consequence of this force, but you're not changing the magnitude, you're not changing the kinetic energy, and also that means a delta, the change of the absolute value of the speed remains constant, but the direction is changing. So you find here the next gap text on our, and that brings us here to a little more detailed look onto the Lorentz effect or the Lorentz force. So we are looking at, do you have questions on what, but I will a bit elaborate on that. Maybe we'll have after that have another small break. But don't hesitate to ask questions. It's always good if I know if something didn't come across clear enough or so, then I know where to where to add maybe some information and or where to give more explanation or other perspective on something. So we do here now just a very rough sketch in this section here for the detailed calculation and for the exact or explicit solution procedures. I would like to refer you to the lecture notes because this is a bit uh, lengthy here to present it in um, the tutorial, but I want to give you the gist, the essence along, and then you can go for the details also. Even if you don't find all the details here, then on the write down, you will find them in the lecture notes. So we have here the scenario where we have a charge which moves through the magnetic field. It has a velocity v, and we assume the following, and this is no limiting assumptions. We assume that the B field is oriented parallel to the z-axis. So where's our z-axis? Our z-axis is also in this direction here. This is our z-axis. So our B field is some constant times the unit vector in z direction. The B field is static. So that means it is not changing with time. And also the B field is homogeneous. It is also parallel aligned, which we see because it's only in z direction. It is parallel aligned with the unit vector z. We are here in Cartesian coordinates. So we want to see now in view of this Lorentz force, if we send in a particle, what kind of motion will it prescribe along what kind of trajectory will this particle move as we basically let it enter this magnetic field. And for that purpose, we have to go to Newton's equations and see how if we make the balance here of forces, um, what what will result as a motion. So the Newton's equation of motion is that the force is equal to the mass times the acceleration. Yeah, A is here acceleration. Don't confuse it with the area vector, for example. But you see, this is it is when you it's usually quite clear from the context. So this is acceleration. That means that is a temporal change of the velocity. That is dv by dt, derivative of velocity with respect to time. And you have to balance this here. So you have on the one hand side the mass times acceleration, and on the other side the force that is acting, that is taking an impact on that motion, is the Lorentz force. So you see you have here that particle, that charge moving. This is the motion given at the instant t0, let's say. So it has a certain velocity, it has a certain mass, and that is here this part of our Newton's equation. But at the same time, that motion direction or could now be altered because there's a force acting here that is the Lorentz force. And the Lorentz force we've seen on the previous slide, that depends on the charge and the velocity of the particle and the B field. Oh, thank you. Happens. Okay, here it is again. So it depends on Q, on the velocity, and on the B field. This is our equation 3.3. So what is this cross product that we are using here? You know, if you take the cross product of two vectors, then we are, I think we have also covered that in the mathematical recap. So it gives you a new vector which is perpendicular to either of these vectors. So basically, if you think of these two vectors v and b are prescribing in between them like an area, then that third vector would be perpendicular to this and would be also weighted according to the size of this area which is prescribed. I mean, it would give you two edges of a parallelepiped for the two vectors here. So you have the v cross b, you know, that is vx, vy, vz, the components, take the cross product, and now we say our x component of b is 0 and the y component is also 0. Then you obtain here, you take x component would be vy times vb, sorry, vy times b here, minus this one, but this is vanishing. The second component would be vz times 0, nothing contributing, but here there's minus vx times b, and the last component you see that is all 0. So you get force contributions, so this is proportional to the Lorentz force, and you see there are contributions in x and y direction, but there is no component in z direction. Let's insert that now into 3,3. That means we obtain here for the x component an m times delta vx dt times q times vy times b. That would be here the equation here for the x component. For the y component, we get m times y dt, and we take here the second entry here, the y component, that would be minus q times vx times b. So that us is our equation 3,4 according to the script. And then the third equation is m dv z component, derivative with respect to t, and that is 0. So what you have here, you have a first order differential equation, yeah, because you have a one-time derivative with respect to time. So this gives you a first order differential equation for the velocity components. So you want to perform an integration here, and you need the integration constants. So we want to obtain the trajectory of our charge q. And to derive that, we have to do the following step. So we want to derive the trajectory, that means a path along which that motion will continue according to the solution that this differential equation gives us. And so we want to determine the velocity as a function of t, and that velocity is basically the derivative of the position vector here with respect to time. And then we have to integrate. We first determine that, then we integrate, and from this integration we obtain then our r of t. So we need to define initial velocity. So that is always, this is kind of to solve any partial or any differential equation, or for that matter also for partial differential equations, but this would be just here a differential equation. You need to provide, in this case, the initial starting conditions or boundary conditions. So you want to define the initial velocity at the starting time t equal to t0. Here, for really close details, I want to refer you to the printed lecture notes. So, but we can now look at it qualitatively, see what we're expecting. So if we are looking at we have put these three first order differential equations, 3.4, 3.5, 3.6. Well, let's start looking here at 3.6, and you see that the temporal derivative of Vz is 0, which leads us to the conclusion that Vz is a constant. That means whatever our Vc is at the time t0, this will not change. It will be Vz0. And this we could also denote as here parallel, in the sense that this here is that Vz here is a component of the vector of the velocity vector, which is parallel to the B field, because the B field is oriented in z direction only. So as a consequence, we see from that initial graph also, the rule here is that you take the right-hand rule. So you have, if you take the finger rule, if your thumb points in the direction of the velocity vector, and if you now look only at the z component, then you see the B field is also in the z component, so that cross product of V and B is vanishing, and there is no force in z direction. So V z is not affected. And that is also what you see here in this equation 3.6. So Vc is not affected. So we can also call that as a V parallel vector that is parallel to the magnetic field. So it is not affected by the B field. And not affected means neither in magnitude, of course, and direction, neither. Otherwise, it, of course, would be affected. So you have basically here your B field, and you have your charge Q, and it is moving here in Vz with the velocity Vz not 0, and it keeps moving. So that is the first point. Now we want to see what's happening in the xy plane. So we have looked at z direction, that refers to equations 3.4 and 3.5. And here we are actually moving perpendicular to the B field, which is oriented in z direction. So our perpendicular component of the velocity vector is Vx as a function of t, Vy is a function of t, and 0. Yeah, this is our perpendicular. You see, whatever we had at z, that we have split off into the parallel component up here. This is our z component. This here is our perpendicular velocity vector, that is whatever is perpendicular to the B field. So what we have concluded earlier is, when we were looking at the work integral, we were seeing that the Lorentz force is always perpendicular to the direction of motion. And if you integrate a work, then you integrate the work over the integration path, or basically onto your path of motion. But now, since they're perpendicular, this Lorentz force is not contributing to your energy. It does not add anything, it does not take anything out. And as a consequence, we have said, because we know that there is no work performed on Q when it is moving in a B field, that means also that the magnitude of the velocity remains constant. Thank you. So no work is performed. So if no work is performed, kinetic energy is also not altered. So the velocity has to remain constant as magnitude. The magnitude of the velocity vector is constant, and that means the initial velocity is v sub 0 at t equal t0, and that remains the same. So we have an initial velocity, that is v naught, at a time t equal t naught, and our magnitude remains constant. That means the magnitude of the velocity vector is adding up the x component squared, and so take the magnitude squared here, so we get vx squared plus v squared, vy squared, and vz squared. So these remain constant. This is the square of the initial velocity. So as for vz, we have said that is also constant because it is not altered. So there is initial velocity for z that remains constant. So as a consequence, you can also say that vx square plus vy square is v0 square or v naught square minus the, that here is z0 minus z0 square, or however we denoted it earlier. Yeah. So this, I think this probably looks familiar. You have vx square plus vy square is a constant. If you have such thing where you have x and y, and you have x square plus y square is constant, then you just get a circle here. With that circumstance, we want to take advantage of that. We know that x square plus y square is constant. That gives you a line on a circle that also then applies here for our vx square plus vy square. They are constant. And because of that, we see that the motion of that particle in the xy plane is circular motion. Now, if you have here the B field, and you have here your charge q, and it comes at an initial velocity, and you know that this initial velocity is basically defined by that perpendicular constant. So this is overall velocity minus the z component squared. You take the square root of that again. Then this will give your velocity component, which is in this plane perpendicular to the B field. And now I want to, for the detailed solution, you have to look, because it's a bit more lengthy, into the notes. But I want to reason for you how this could look like, or this will look like. You basically have here circular motion, and this here is your B field, the lines, and this is a circle, and it has a radius r, and it has a cycle frequency. You have here that resulting velocity vector. If you look at the angle of that vector with the B field, it will be 90 degrees. And now, yeah, you have this angular motion, and that particle will actually go in circles, and it has this frequency that it takes to circle around. That is this omega here, which I denoted. This is kind of also called then the gyration frequency. And it will give you also a certain radius, depending basically on the speed, that on the velocity, on the perpendicular velocity, and on this gyrational frequency. So, however, to look the details for how to solve for the velocity, and also how to solve for r, I would like to refer you to the lecture notes. So the charge is rotating inside this magnetic field, the flux field. and it does that in the plane which is perpendicular to the orientation of the magnetic flux. So this happens at a frequency, and that frequency we denote with omega, and that frequency is given by the charge value, by the value for the magnitude of the magnetic field here, and by the mass of that particle. This is equation number 3.2, and this here, this omega, this sign here is an omega. It's a capital omega, and you know that this one here is also an omega. This is a small omega. It's a bit similar to the W, but it is it's not pointed at the bottom. So in this omega, this is the gyrational frequency. Gyration, that is basically means to turn, also from Greek. The gyrational frequency, and this as a frequency is basically 2 times pi over f. That is a regular frequency as in per second, and the gyrational frequency gives you 2 pi over times f, 2 pi over some seconds. So what about the radius? Well, now there's in a gyration you also have a radius, and that depends on the velocity that you have and on the gyrational frequency. And this relation I want to give you here, this is okay, it doesn't stop. You have the gyration, that is basically we want to look at the rotation radius, and that is given as this is our velocity component in this plane perpendicular. That is the one that is relevant for that gyration because that determines the force, and therefore enters into the equation for the gyrational frequency. This is our equation 3.8, and if you want to have a visual on that, you have here a circle, and you have on the one hand a force acting to the outside. That would be like your centrifugal force, if you take that in analogy to the gyration motion. You have a centrifugal force, and that basically this centrifugal force is given by our Lorentz force. That is now proportional to the perpendicular component and the mass. Respectively, our force is the one, the Lorentz force is the one pulling inside, opposing that one here. And you have here our velocity magnitude. And if you look at that, then you have a velocity, and the gyrational frequency that tells you that's 2 pi times f. So that is, if you look at the distance that is covered in per second, that is basically taking the gyration, the gyrational frequency times the radius, and hence that would be the distance covered in a time interval. So that would be your velocity. And so that is the reasoning why the radius here that is prescribed by this gyrational motion is given here by dividing the velocity, the perpendicular component, or the magnitude of this perpendicular component through this gyrational frequency. And to depict what you can then expect from this is you actually obtain in the plane a pure circular motion as long as your particle remains in this constant B field. Of course, it could happen that your particle enters and it cannot enter into a full circular motion because it is leaving the B field beforehand. But in general case, Okay. The general case is you have here for your velocity vector component that is perpendicular. This is our B field here. You have, so this is a B field, and you have a component that is in parallel for the velocity vector. So you have a total velocity vector, and you can prescribe here a vector alpha that is measured towards the z-axis, and this whole coordinate system here is Ex. And now as your particle enters here into that field, it has now these two components. It makes a circular motion. It makes a circular motion in the xy plane, but it also has a component in the z direction. So that is not altered. That keeps moving just from, if you just look at the z component, it keeps just moving there in that at a constant speed, as we said, and that would be the initial speed as it enters into that field. But in terms of the xy component, it starts within that magnetic field to follow the trajectory of circles, but superimposing that z component, you get a trajectory which spirals here in this direction. And this would be the general case where you have an angle between the velocity and the B field, which is neither 0 degree and it is also not 90 degree, right? Because that would be the angle of our alpha here that I entered here. This is our alpha basically here. So if you are at alpha 90 degrees, you're purely in the plane, and you just circle in one plane along a circle with constant radius. And if you are with an angle which is alpha equal to 0, then you just go straight parallel along the field lines. So this means, let's add here some information. So V parallel, for that, there is no change in magnitude and direction. That remains constant. So the V parallel remains constant. But for the V that is perpendicular to the field, you have a circular motion. And that circular motion is in the plane perpendicular to the B field. And then you superimpose these two, and that yields you this spiraling, this helical motion, the superposition. Now you could have different scenarios where your field may be arbitrarily oriented. Right now we just had it arranged in the in such way that it is the magnetic flux, the B field, is parallel to the Z. But what happens if that is not the case? Let's assume you have a B field which is somehow oriented like this. And now you had a charge which is coming in here, and it has a velocity vector that you can split up here into, again, one component that is perpendicular and one that is parallel to the V field. Then you would, with respect to whatever is perpendicular, there here it would prescribe this circular motion. But at the same time, you also have your motion contribution in the parallel to the B field. So you superimpose these two motions, make a superposition, and then you get now for, again here, a helical motion for your particle. And also it could be that you have somehow your field lines being bent, so you don't have field lines that keep their orientation over the entire space, but they are being bent like that. This is your B field. And if you look at your charge here, it comes in with a velocity V, then you can again decompose the velocity vector into a contribution. Well, you have to decompose it here into the component that is aligned, perpendicular, and into a component, I mean, one that is parallel and one that is perpendicular. And you will get also circular motions here then in a tilted field. So the circular motion will be always with respect to the component that is perpendicular to the B field, and in the other one it will move on straight. So you get some, also here you will get some helical motion even if the B field is tilted over space. So you can expand that also to the scenario where you have a current distribution, the Lorentz force. And I mean, are you comfortable with that, with this helical motion from the concept here? There, so the thing is, you have a Lorentz force which is acting only on the component that is perpendicular on it, acting on the charge, but only with respect to that velocity component perpendicular to the B field. And in this direction, you will, due to this force, obtain a circular motion, while in the component of the vector that is aligned with the B field, there's no force acting on it. And in the end, you get this helical motion if the B field extends large enough. But the force depends also on the charge, and it could be that your charge is not so maybe large, so it might make a trajectory which is only slightly bended. And of course, it has to remain in the magnetic field in order to experience this Lorentz force. Otherwise, it might also, you might also describe a bending, and it might leave the magnetic field without completing such a complete gyration. But if it stays in the B field, then you will get this gyrational motion. And in particular, if there's a parallel component in the velocity vector that will turn into such a helical motion. And the line of reasoning is, we didn't go into all details, but we were looking at the differential equation and we're reasoning what has to happen there. We didn't really solve for it and integrate. We could solve here for the velocity, and then based on the velocity actually get the actual trajectory by integrating over it. But our reasoning is here, if you look at the components perpendicular, we know the Lorentz force is not adding any energy to the system. Our total velocity in the perpendicular plane, perpendicular to the B field, must remain constant, and for that reason we have a circular motion. And this circular motion in the perpendicular plane is superimposed to that straight constant motion parallel to the B field, and you can obtain that gyrational frequency when you solve these equations, that is governed by your, that is here the equation 3.2, that is governed by the strength of your field, and it is given by the your charge, how large the charge is, but also, of course, the mass of the charged particle plays a role in that. Next thing will be that we have been looking at the force now, the Lorentz force for a single particle. The next thing is we will expand that to charge densities. And then we want to see what happens if we have, for example, wires which are where there's a current flowing through it. And if this wire is immersed in some magnetic field, then also some, because this force will act on all these charges in the wire, so that the whole wire will experience also a force. This will become also then interesting if you think of the applications like building an electro motor or the like, there this force is basically giving you the foundation for this. I think I will, this is a little bit of outlook, so I think this is a good time to call it now a day. I mean, not a day, but the lecture. At least we'll have a tutorial afterwards. And if you have questions, please, anytime. Thank you.